The next type of isomer category that we will be investigating are stereoisomers. Stereoisomers are different than constitutional isomers in the fact that we are not changing the bonding pattern in order to create a different structure. What occurs with stereoisomers are there are carbons that are locked in space, or they're fixed in space based off the bonds that are formed. So single bonded carbons can rotate freely around those bonds. Double or triple bonds, or cyclic structures, puts carbons in a fixed or static location that prevents them from rotating freely. From there, the groups that are directly attached to those fixed carbons are also fixed in space. The first type of stereoisomers we'll be investigating are cis or trans. Cis or trans designation alerts us to the groups and where the groups that are bonded to those fixed carbons are located in space. In order to be a stereoisomer, we have to have carbons that are fixed in space or are static. We then need to determine how the groups are arranged around those fixed carbons to determine if a compound has cis or trans designations. We need to look at the groups that are bonded directly to the fixed carbons. What I do for cis or trans is I'm going to first draw a vertical line that separates the groups of the two carbons that are participating in the double bond or in the cyclic structure. What we want to identify is what are the groups or atoms attached to one of those carbons. These need to be different. So if we look at this first atom, these are both hydrogens. Those are the same. That means that this structure is not a stereoisomer. It is not going to have cis or trans designations. What is required is that the two groups bonded to that fixed carbon need to be different. So here, let's say this is group A, this is group B. One's a methyl, one's a hydrogen. Those are two different groups. That is required to know whether or not we would have a cis-trans designations. And we need to do that for both sides of the locked carbons. If we answer yes to both of these, we then look at that carbon plane where the locked carbons are at, whether it's the double bond or the cyclic alkanes. So I lay that line down horizontal because this allows me to track where the longest parent chain is at. Let's say that the carbon chain or parent chain goes from A to C to C to X. That puts these groups on the same side of the locked or fixed space. This designates a cis stereoisomer. If we go from A to C to C to Y, these groups are opposite. And because they're opposite or across from each other from that fixed point, this is going to be trans. So looking at these with true chemical structures. Step one, we are going to make that vertical line slicing where our fixed carbons are at here. That is that double bond. Looking at either side, so I've got a methyl group and a hydrogen. Those are different. I've got an ethyl group and a methyl group. Those are different. This compound thus will have cis or trans stereoisomers. Next step is to find that parent chain. The parent chain here must include that double bond, or it would be the cyclic ring. So looking at where those groups are at in relation to the fixed carbons, they are both above or on the same side of that double bond. Another way to look at this, in case we don't have just carbons, we might have heteroatoms like oxygen, nitrogen, or our halogens, is look at the electron density. Follow the electrons. So here we have a map of electron potential, so the potential of finding electrons. If you notice, the majority of the green space or the cloud is on the same side of that double bond, so that is another way in which we can visualize this cis designation. Now let's look at the other form. Crossing through that double bond, let's see, we have a hydrogen and a methyl group. Those are different. We have an ethyl and a methyl group. Those are different. So we know we're going to have a potential cis-trans designation for the stereoisomer. Find the longest parent chain so we can follow those electrons. Lay that vertical line down horizontal so that we can look at the groups in relation to those fixed carbons. So we've got that methyl group that is, let's say, below that double bond, and we've got this ethyl group, let's say, above. They're going across that bond, which is what gives us the trans designation. And if we look at the map of electron potential, we can see how the electrons are more evenly spread out across the entire molecule, and the cloud is not just on one side. And that will dictate reactive properties as well that we'll talk about throughout the semester.